So just to clarify, why is it the moment is about the z-axis? Okay, so if you look at a moment about z and the rotation about z, the curvature is in the same orientation. Like look at this curvature and look at this, they're the same, right? That's why it's moment about z. Okay, now, so when that's the case, right, if we look at stress x, stress in the x direction at point alpha, and we know that it's going to be what? Compressive. So the only way for equation 1, okay, so for the only way for equation 1 to be compressive is y must be what? Positive. Okay, y must be positive, right? So y must be what? Positive, right? So from here you can write out stress x alpha at point alpha is equal to minus mz over izz, right? So this is the root formula, but now we know that y is what? Positive. So the outcome will be a minus mz over izz multiplied by y. So compression, right? Because positive and negative give you what? Negative, right? Or negative and positive give you negative. Okay. Now, if we were to look at stress x at point beta, as you already know, is going to be what? Tensile. Okay. So when it's tensile, y over this case has to be what? Negative. Okay. Y has to be negative. Right. So how does this work now? So we have stress x in beta. So this is equal to minus mz over izz multiplied by negative y. Okay, so this will be equal to mz over izz multiplied by y. Okay, so we know that this is positive, right? That's negative. So that's why it's tensile. So now, when is y positive or when is y negative? So if you look over here, right, I'm going to draw a point over here. And this point is known as our center of curvature. Okay, that's our center of curvature. Okay, right? It's not on the bottom side, it has to be at the top, right? Because of how the structure has been bent. Okay, so relative to the centroid, I repeat again, relative to the centroid, watch this arrow I'm going to draw. Okay, so relative to from the centroid, anything that is above the centroid, y is positive. Anything away from the centroid, okay, y is negative. Okay, I want you all to see that. Okay, so that's how we define what is compression or tension. Now, that is theoretically what's happening. I'm going to teach you an easier way to remember. Okay, and the technique I'm going to teach you is going to be based on the moment vector. Okay, so we're going to look at the moment vector. Okay, we're going to look at the moment vector. So this is how the moment has been applied. Okay, the head, or I'll call it the yeah. So the arrow, right? So this is an arrow. So the head of the arrow is always what? Compressive. The tail. Okay, so this is the tail. This is the head. Is always going to be what? Tensile. An easier way for you to what? Remember, because later on we're going to do this in 2 axes. Okay, not just 1 axis. We're going to work on 2 axes, and later on Much later on, we're going to have compound loading. You have moments and you have torques, okay, and you have torsion coming in. You have shearing stress. Too many things, too many formulas to remember. I want you to remember as easier way is the head of the moment vector is always in compressive. The tail end is in tensile. Okay. Any questions so far? Anyone? No, I don't hear anything. So what I'm going to do now, what will happen now, right? I'm going to switch over. Oh, are you still copying or can I go to the next slide? If you're copying, let me know. So I don't think anyone is copying or not, or you guys are ahead of the copy. Now, if the deformation is the other way now, right? So we're going to draw the deformation. So this one is smiling face. We have the deformation in the other direction now. Okay, so what if now the deformation is going this way? Okay, where this is our, again, the points did not change. So this is point A, point B, right? And point C. Okay, and then this is our centroid. Okay, so this is our centroid, right? And again, I'm going to label at this point. This is going to be our alpha, and at this point, this is going to be our what? Our beta, right? That's our alpha, and that's our beta. So if you look over here, right? So now we know on the outside, this is in tensile, or at alpha with tensile. On beta, this will be what? Compression. Okay. So if we were to write this thing out like what we have written before, so we know that stress X, right? And at alpha now is going to be in a tensile mode. So for equation 1 to be tensile, Y has to be what? Negative, right? So stress X alpha is equal to minus mz over izz. And your Y has to be what? Negative. So that's why it's equal to positive mz over izz multiplied by Y. Okay. Whereas in stress X beta, right, we know that it's going to be a compression. So Y has to be what? Has to be positive, right? So stress X at point beta is equal to minus mz over izz. Now the Y is positive. So the outcome is you get minus mz over izz multiplied by Y. Okay, so mathematically, what is happening? Okay, so if this is a center of curvature, right, the center of curvature switches now, yes or no? Right, pointing towards the center of curvature, right, Y is positive, away from the center of curvature relative to the centroid, Y is what? Negative. Okay, now if we were to draw the moment vector again, right, this is how it looks. Right, moment vector. So again, like how I teach you to remember, the head of the moment vector is going to be compression. The tail end of the moment vector will always be what? Tensile. Okay. So now with both configuration, what are we actually calculating? Okay. So I'm going to, any questions so far again? Okay. Anyone? No? Okay. So if we, again, I'm going to copy this diagram. Okay. So this is our loading, right? So if I draw a configuration or transformation, this is our X, this is our Y, this is rotation about Z. Okay. So now I'm going to draw a cross-sectional view. Okay, so cross-sectional view. Okay, cross-sectional view. So if I draw cross-sectional view, now this is how it looks. Okay, so watch the transformation. So this is my Y, this is my Z, and this is my rotation about X. Okay, and then we draw the cross-section. Okay, so this is our cross-section. Right, there's cross-section, and this is the position of the centroid. Okay, because it's rectangular, the centroid is exactly at the center. Okay, so this is our centroid. Okay, and for this case, I like to highlight centroid is acquired geometrically. Okay, so this is based on geometry. Okay, right. So if the structure is loaded this way, okay, so we know that the deformation looks like this, right? We know the deformation look like this, right? So this is our moment about Z. So this is our deformation pattern. All right, and we also know that this is also our centroid. Right, so if that's our centroid, so if we now were to draw, okay, we're going to apply stress X is equal to minus mz over izz multiplied by y. Okay, so I'm going to sketch, okay, the stress X distribution. Okay, so I'm going to copy this figure. I'm going to copy this figure. Okay, so this is a sketch. So this sketch, how does this sketch, or what does this sketch actually means, or how to sketch this sketch? Okay, so we have an axis. So this axis over here is our stress X axis. Okay, and then we have our vertical axis. Right, so vertical axis over here is your Y. Okay, why? Because if you look at this transformation over here, let me copy the transformation so you can see clearer. Okay, so if you look at this transformation, okay, so this is the Y. Okay, so this is Y. So the 0 over here, right, this is relative to your what? Centroid. Okay, this is relative to your centroid. So we know when we apply stress, so over here, right, that will be our Y max. right? Down here, this region will be our y what? Minimum, right? So by looking at how the structure has been deformed, so we know that this is compression.